Hello and welcome to Mathematics with Simon. I'm Simon. Today we're going to look at logarithms as part of the A-level mathematics syllabus. So what is a logarithm? So taking a log to the base 10 is the inverse of raising 10 to the power. So if log to the base 10 of b is c, that's exactly the same as saying 10 to the c equals b. So log 10 takes you one way and 10 to the power takes you the other way. Log 10 takes you from b to c, and then 10 to the power takes you from c to b. So log to the base 10 of 10 to the x is x, and 10 to the log to the base 10 of x is x. Or log to the base a of a to the x is x, and a to the log to the base a of x is x. So log to the base a of x is the power that we need to raise a to return the value x. For example, log to the base 10 of 1,000 is 3. Log to the base 2 of 16 equals 4. So 10 to the 3 is 1,000. 4 to the 2 is 16. No, 2 to the 4 is 16. 4 to the 2 is 16, but 2 to the 4 is 16. This is an interesting learning moment. So log to the base 4 of 16 is 2, and log to the base 2 of 16 is 4, because 2 to the 4 is 16 and 4 to the 2 is 16. Wow. What fun. This is an exponential curve, y equals 10 to the x. So it's fascinating, isn't it? Because it stays low for a long time and then it really takes off around 3 and 4. So exponentials really take off quickly. So for every x value, the curve is positive, although for big negative x values, it's very small, but it's always above 0. And this is a log curve. Y equals log to the base 10 of x. So what's interesting here is as x tends to 0, then y goes down to minus infinity, and then when x gets to 1,000, y is only 3. When x gets to 10,000, y is only 4. So logarithms have many fascinating and important properties. So the first one is that the log of a plus the log of b equals the log of ab. Log of a minus the log of b equals the log of a over b. Log of a to the b equals b log a. So just a quick example of log a minus log b equals log a over b. So say it was base 10. You have the log of 1,000 is going to be 3. And then the log of 100 is going to be 2. So 3 minus 2 is 1. And that's equal to the log of 1,000 over 100, which is the log of 10, which is 1. Okay, so that's an example. But these laws kind of work with logs. We're going to prove them because we like to prove things in maths. So c to the a times c to the b equals c to the a plus b. This is a basic law of indices. I'm going to take the log to the base c of either side. So on the right hand side all we have is a plus b, because log to the base c is just the inverse of c to the power. Then we're going to rewrite a as log to the base c of c to the a, and we're going to rewrite b as log to the base c of c to the b. Then we're going to swap c to the a for x and c to the b for y, and we have our law. Now what's really interesting just to note here is that x and y can only be positive, and because exponentials are always positive, and that's important because in what we're looking at the moment, logs only make sense on positive numbers. They don't make sense on negative numbers in this video. There are ways of making them make sense on negative numbers. That's another video. So here's another one. C to the a divided by c to the b equals c to the a minus b. We're going to prove this. So we take logs to the base c of either side. Then again, we're going to rewrite a as log to the base c of c to the a and b as log to the base c of c to the b. We're going to substitute c to the a as x and c to the b as y. And we have our result. Next, we're going to prove log to the base c of a to the b equals b times log to the base c of a. So firstly, a to the b is just a times a times a times a, b times, which by the previous rule is just log to the base c of a plus log to the base c of a plus log to the base c of a, b times, which is just b log to the base c of a. Okay, so now we're going to look at another thing called the change of base formula. So this is a really clever thing. Log to the base a of b equals log to the base c of b divided by log to the base c of a. So as long as we have all of the logs in one base, say base 10 or base e, then we can calculate logs in any base that we want to. So the base that we currently have is c, and the new base is a. The base we want to move to is a. We'll talk a bit about e later on. So let's prove the change of base formula. So firstly, as we know, a to the log of base a of b equals b. Now we're going to rewrite a as c to the power log to the base c of a. I know, it looks like unnecessary complication, but it's going somewhere. Then we can simplify the left-hand side because x to the y to the z equals x to the yz. So we're manipulating the left-hand side. And then we're also going to rewrite the right-hand side. Instead of b, we're going to call it c to the log to base c of b. Then we are going to take logs to the base c of both sides here. So what we get is log to the base c of a times log to the base a of b equals log to the base c of b. Divide both sides by log to the base c of a, and hey presto, as we like to say in the world of mathematics, log to the base a of b equals log to the base c of b over log to the base c of a. So in some sense you could say the change of base formula is the log equivalent of x to the y to the z equals x to the yz. Okay, since we were talking about change of base, a very important logarithm base is the base e, which is this very long decimal, which goes on forever, by the way. I mean, actually, that's an infinite decimal, so you should write it with dots afterwards. It's an irrational number, so it can't be expressed as the ratio of two integers. It's not even an algebraic number. So it's not even the solution to an equation involving integers and powers. It's what we call a transcendental number. So why do we want to use this as a base for our logarithms? Well, it's got all sorts of special, wonderful properties. Firstly, here's a slightly more memorable and meaningful expression for e. So e is 1 plus 1 over 1 factorial plus 1 over 2 factorial, which is 2, plus 1 over 3 factorial, which is 6, plus 1 over 4 factorial, which is 24, plus 1 over 5 factorial, which is 120. So where did all of this come from? Well, we remember the integration formula. Integral of x to the n dx is x to the n plus 1 over n plus 1 plus c. If you haven't done this yet, don't worry, just go with it. So what about when n is minus 1? Well, it kind of all breaks down then, because you end up with x to the 0 over 0, because minus 1 plus 1 is 0. Which doesn't really make sense, although we do have a video on 0 to the 0, but we're not going to go into that now. Basically, it's kind of indeterminate or confusing. So what we actually discover is the integral of 1 over x, or x to the minus 1, is log to the base e of x plus c. Log to the base e of x is also written as ln of x. It's another way of writing it. And e has all this amazing connected property that if you differentiate e to the x, you just get e to the x back. So it is its own differential. What's another example of a function that's its own differential? 0. That's an example, but it's a very special property, which means that if you take n derivatives, you still get e to the x because you just keep differentiating and it just stays at e to the x the whole time. So it's equal to its nth derivative for all n. Also true of 0, but 0 is a slightly odd function. It's slightly degenerate, the constant function 0. So what this means, if you use the sort of Taylor or Maclaurin expansion, what this means, again, if you don't know about that, don't worry too much, but it's a matter of fact, e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial going out to infinity. Beautiful and amazing series. And we've just calculated the denominators, which are factorials. So inverses are a recurring theme here, and they're just very important in mathematics all the way through. So taking the log is the inverse of the exponential. Integration is the inverse of differentiation. So we need integration to discover log to the base e of x, because we had to integrate 1 over x. And then we also find e to the x is a very special function because it's equal to its own derivative and hence all of its derivatives. Wow, that was a journey. I hope you liked the video. If you do, please hit the like button. You're very welcome to subscribe and hit the notification bell. I'd love to hear your ideas, and most of all, I hope you enjoy your mathematics.